It gives me great pleasure to introduce Dr. Elizabeth Mahony from the University of Sydney, who's going to talk to you about supermassive black holes. So cool. So just enjoy and listen up. Thanks.
Now, before I jump straight into talking about black holes and all that crazy stuff, I thought I would start with a short video, if I can get YouTube to come up. Come on, YouTube. That just it puts everything into perspective. So it always reminds me of just, our place in this universe and how big the universe really is. So what we're going to see here, this is what they call one of the powers of 10 videos. So we're going to start on a scale of about 10 centimeters. So this is, size of someone's face. And zoom out, each time adding a 0 at the end of that number. So zooming out by a factor of 10. And very quickly, you'll see how quickly we can leave Earth, leave our solar system. Oh, there's music. Okay. So now we're at already 10 meters, so we're zooming out, adding a 0 on each time this lady happens to be lying on the floor in Google in San Francisco. She must work at Google, so cool for her. So now we're zooming out again, we're starting to see all of the US, the Pacific Ocean. So now we're at 1,000 kilometers, and we're zooming, and very quickly now you see there's Earth. And soon you'll see the moon come in, and you'll see how quickly it's all changing. So now the Earth is this tiny little dot. And only now you're starting to see the planets come in. So look how small Earth is compared to our closest planets. There's the sun in the middle there, then you see in the solar system. So now there's Pluto, a spacecraft we launched like 20 years ago. So now this is the size of our solar system. So still we haven't even got to our closest star, which starts coming about now. So they're our closest stars, which are over 4 light years away. So that means that besides the sun, so the sun is obviously our closest star, the next closest star is over 4 light years away, so it takes 4 years for the light to reach us. Now we're in our Milky Way, and then you're going to start to see other galaxies coming into view. And then eventually we zoom out until we see the view of the whole universe. So these are our local clusters, and each of those purple dots is a galaxy, like our Milky Way, and each of those galaxies can hold billions of stars and potentially billions of planets like Earth. And then we go all the way back in, and it gets much quicker here. Sorry, I hope no one gets motion sickness, because there's lots of these zooming videos coming, I'm sorry. When you study space, you end up zooming in a lot. Okay, so now we're getting close to Earth, flying back in. So that was the main thing I wanted to show you. I'll actually keep this video running because I think it's just really interesting. It's not what I personally study, but now we're going to go back down to 10 centimeters, and instead of zooming out, we're going to zoom in. So now we're going to go into her eye and go, instead of increasing, adding a 0, we're going to add a decimal point. And so this just gives you an idea of the world of science you can study. You can go really focused, and if you want to go into biomedical stuff, you can study DNA and chromosomes and things that I know nothing about. And so this will come up again in my talk later, but now we're at the scale of an atom, or subatomic particles. So these are the smallest scales we know. Compared to that of what we know of the universe, there's a huge wide range of scales that we need to explore. Okay. Oh, and now it's going to zoom out again into the face. That's fine. Zooming out. Okay. All right. And we're back at this smiley face on the lawn in Google. Okay. So I really like watching those videos because it really reminds me of, why I do this. And the world is a really interesting place, and I'm really interested in just, expanding our knowledge, finding out why things work. Why do stars behave the way they do? Why do galaxies behave the way they do? How does DNA work? I don't know the answer to that one, but I hope someone does. So I'm going to start off talking about our Milky Way. This is our galaxy. If you go out into the countryside, get away from all the city lights, hopefully you can look up into the sky and see something like this. So you see this milky band of light stretching across the horizon. So this, of course, is our own home galaxy. And our Milky Way, like all galaxies, is made up of three key ingredients. You have stars, which are all these little white dots. So in our Milky Way, there's over 100 billion stars in our galaxy alone. You also have lots of dust. So these are all these kind of black areas you see across the galaxy. And this is really important because it's this dust and gas which is the raw ingredient that goes into forming stars. So this is basically where all our stars are born, from this dust. And lurking in the centre, which you can't really see here, there is actually a supermassive black hole buried at the heart of all large galaxies. So if we look at our Milky Way, I have another zoomy video, then I promise this is the last one. So now, this is work that astronomers have compiled over the last few decades. Now we're going to zoom in to the centre of our Milky Way. And this is all this is real data. This is all taken from astronomical telescopes around the world. So to get to the centre of our galaxy, you have to zoom in quite far. So you zoom in, and you zoom in, and you use bigger telescopes, and you use bigger telescopes to get further and further to the centre. And then eventually, what you can do when you get to this level, so these are now individual stars right at the centre of our galaxy, and they tracked them for many years and worked out the orbits that these stars were doing. So you can see them moving around. So these are the actual observations, and then they were able to model that. And so then they could work out the orbits. So the orbits are shown in blue there. This is the computer model of the orbits. And they were able to work out there must be something in the centre here that is really massive, has a huge amount of gravitational pull, but we can't see it. So this is just an image, like a circle. There's something here, but we can't see it. So we know that that's a black hole. And this black hole in our Milky Way is about 6 million times the mass of our sun. So if you take 6 million of our suns and squash it down into a space roughly the size of our solar system, that's what the black hole is equivalent to. So that's just our galaxy. But our Milky Way, as you saw in that video earlier, is just one in a sea of thousands and thousands, probably billions of galaxies. So this is an image, again, this is really what the sky looks like. This is an image taken from the Hubble Space Telescope. So this is a telescope that's orbiting the Earth. And it basically just took an image, it stared at one patch of sky for a really long time, I think like months or something ridiculous. And then when they looked at the image, they saw something like this. So instead of each of these points being just one star, each of these images you see here as an entire galaxy. Even these like little white, even all these faint things that you can barely see, each one of those is an entire galaxy. And as you can see, they all look completely different. So some galaxies are spiral-like, some are just big fat red blobs that are just a bunch of stars hanging out together. You can see there's a range of colours, some are reds, some are blue, and we still don't understand how galaxies come to look like this. This is what I study, trying to work out why can galaxies look so different? How can some of them look really blue? How can some of them look red? And how do they all stick together? So how do they form and how do they evolve to look like this, like they do today? So the reason I study supermassive black holes is because we think it's the black hole that plays a really important part in how these galaxies grow and evolve. So as I said, in the centre of each of these galaxies there's a supermassive black hole. Now in some of them, when you have a lot of stars or a lot of gas that gets very close to the black hole, so this doesn't happen in our galaxy, but in some galaxies, if there's a lot of dust and gas, it can get sucked into the black hole. And so it does that by forming what we call an accretion disk. So the gas gets spirals into the black hole, and this gas gets very hot and radiates a lot of energy in this accretion disk that can sometimes outshine the entire galaxy. So you imagine the size of this, it's called a supermassive black hole, sure, but on the scale of an entire galaxy, it's pretty tiny. And this thing, there's so much energy there that it can outshine all the stars combined in that galaxy. And so this is what we call an active galaxy. And this is where we think that the black hole plays a really important role in regulating how the galaxy grows and evolves. So in some cases, we also see these radio jets come out of these galaxies. And that's what I study. So on the left here, this is just a model of what we think is happening because we don't quite have the telescopes yet to be able to see supermassive black holes at this resolution. But on the right is a real image taken from a combination of an optical telescope and a radio telescope. So you see here, this is the optical galaxy, and these radio jets are coming from very close to the black hole, but they're launching all the way out to be far bigger than the galaxy itself. So this black hole can clearly have a huge impact on the galaxy. Now, one of the other things I found really interesting about these type of galaxies is that they look very different in all different wavelengths. So depending how you observe them, you see something completely different. So this is one galaxy. This is one of my favorite galaxies. This is called Centaurus A, and it's actually the closest radio galaxy to us, but that's still like 1 million light years away. So these images that we're seeing now, the light actually left this galaxy 1 million years ago. And if we look at this galaxy with an optical telescope, we see this yellow image here. So it looks like a galaxy like we saw in those other pictures. It's a yellow cloud of stars, pretty much. And you see this has an interesting feature, though, that it's got this kind of dust lane crossing the middle. So it means that there's a lot of dust and a lot of gas there, which potentially can mean that it can form more stars. If we look, say, with an X-ray telescope, that's when you see this blue image here. And that just is like showing you where there's lots of hot gas around the galaxy. So if you just looked at that image, you'd barely even say that's a galaxy at all. That's just some kind of blue smudgy stuff. But it's all associated with the same galaxy. And then when you look at with a radio telescope, you see these green jets here. The colours are false colours, by the way. The radio jets aren't actually green. So you see these radio jets that are coming outside from close to the supermassive black hole. And then we can also look for the hydrogen gas. So we do that by looking for the spectral transition of the hydrogen atom, which occurs at a wavelength of 21 centimetres. That's why it says the 21 centimetre image there. And again, that's picking up all the hydrogen gas and dust in the galaxy. And you can see how nicely that correlates with this optical image here. So all this hydrogen gas looks very similar to that dust lane we saw in the optical image. So that's what active galaxies are. This is what I study. These are my favourite things to look at. But that leads us to the question of how do we find them? So this is our electromagnetic spectrum. And depending on what wavelength you want to look at, you have to use different telescopes. So for example, this is a really good example, illustration. If you want to look at what this galaxy is doing in gamma rays or X-rays, then you need to use telescopes that are in space, because those gamma rays and X-rays can't propagate through the atmosphere down to the surface of the Earth. On the other hand, in the optical, we know we can see optical waves, because that's how we see the stars in the sky with our eyes. So then we have lots of optical telescopes, and those you can use on Earth. They like to put them on mountains to avoid a lot of the atmospheric problems. And then you'll also notice as you go to longer wavelengths, so infrared, again, you have to go back up to space because the ionosphere blocks a lot of that out. But then when you get to radio, you see this huge frequency range where we can, again, observe these radio waves from space, from the surface of Earth. And so this is where we build all our radio telescopes. So the radio telescope that I work on is a new telescope that we've built out in Western Australia, and it's called the Australian Square Kilometre Array Pathfinder, or ASCAP. So what this is, it's an array of 36 radio dishes that look like that. So they just look like big satellite dishes, effectively. And it's been built out in the middle of the desert in Western Australia because we want to get away from as many people and as many mobile phones as possible. So it's great that we can detect these radio waves from Earth, but turns out that things like your mobile phones, your digital TV channels, satellites, GPS, all of those are much, much brighter than anything that we want to observe in space. So we need to go to these locations, such as in the outback, where not many people live. And actually, if you do go to this place, you can't take a mobile phone. You can't have any mobile phone, no Wi-Fi, no GPS, nothing like that. Because we really want to be able to see what's coming from space and not be confused by everything on Earth. So it's kind of like you don't want to build an optical telescope in the city because all those bright lights just blind you and you can't see anything from space. So this is ASCAP. This is a new telescope that's being built in Western Australia, and we basically link up all 36 dishes and use it as one giant telescope to study what the sky looks like at radio waves. Now, the really cool thing about this new telescope is how much of the sky it can see at once. So to give you an idea, this is the size of the full moon on the sky. So imagine you're looking up at the sky at night and you see the full moon, and it looks about that big. If we now overlay what our new radio telescope can see, it can see this much of the sky at once. So if you just imagine that size, the scale of the full moon, I think it's about 30 full moons that you can fit in one pointing of the telescope. So in one night, we can observe a huge fraction of the sky. And when you do that, you get images like this. So again, this is a real image coming from a radio telescope. And each one of these white points is radio waves coming from a galaxy. So where you see a white dot, that's telling you that there's a supermassive black hole in there somewhere producing these massive radio jets. The other thing that we can do with this telescope is look for the gas in galaxies. So I said before that we can find the hydrogen gas in galaxies by looking for a spectral transition line. So we do that by looking for it in absorption. So we have our radio galaxy in the distance, so it's just like you do in your science experiments. You have a white light, and you take that light and you diffract it through a prism, and then you look at it through a spectrograph, you get a rainbow pattern like that. So it's exactly the same. Our radio galaxy is the equivalent of our white light. And our radio telescope is the equivalent of our eyes. So if there is a cloud of hydrogen gas in the way, then we get an absorption line like that. So if you had told me when I was in year 10 that I would be using my high school physics every day as a job, I never would have believed you. But this is just an example of, the science that you learn in high school is actually really useful and really important, so don't underrate it. The other thing I just wanted to really point out was that, remember that video I showed you right at the beginning, and we zoomed out and we saw all the galaxies and the scale of the universe. And then we zoomed in to go into scales like, the size of an atom. So what we're looking here, we're kind of combining the smaller scales by looking for these atoms in the universe with the bigger scales by trying to study how these galaxies evolve and how they grow. And eventually, we are building an even bigger radio telescope. So if anyone here is interested in astronomy and thinking about being an astronomer, this is one of the telescopes that you might eventually be able to use. So this is called the Square Kilometre Array, and it's going to be a sea of radio dishes like you see here. It's going to be hosted in 2 countries, so it's going to be in Western Australia, and these dishes will be all over Southern Africa. And it's a huge international collaboration, a huge international project to really, progress our understanding of how galaxies evolve and how they grow, and basically, where we came from. Okay. So that probably sounded all very futuristic and, supermassive black holes and galaxies and, oh my God, why do I care? Well, I care because I find it really interesting. But when I was sitting where you are, in year 10, I had no idea what I wanted to do. So I was in year 10 in 2001, which I realised depressingly is probably before most of you were born. Wow, it wasn't really so long ago. But when I was in year 10, I had no idea what I wanted to do. If you had told me that one day I would be an astronomer, studying black holes, what kind of job is that? So, well, it's a very cool job, by the way. So I did work experience. I went to a preschool. I went to a primary school. I thought I wanted to be a teacher. I did work experience there and went, you know what, I actually don't want to do this. So I decided I'd always really liked science and maths. I just was always interested in it. So when it came to choosing subjects for the HSC, I thought, okay, I'll do maths, I'll do physics. I liked music, so I chucked that in there as well. And then English and religion were compulsory, because like you, I also went to an all-girls Catholic school. So I had to study religion. So again, by the time I finished my HSC, I still had no idea what I wanted to do. And so I decided I would do a Bachelor of Science at Sydney Uni, because everyone told me if you do science, it's really broad, you can do all these wonderful things afterwards. I went, okay, I'll do science. I actually enrolled in a double degree. I did a double degree in science and arts. And then when I was in my second year, so I did, history subjects, philosophy. And then when I was in my second year of uni, I actually went, you know what, I don't really like these arts, I'm going to drop arts. And I just stuck with science. And then again, I kept doing all the physics topics and the maths topics because they interested me. I enjoyed them. When I got to the end of my degree, so when I was a third-year student at Sydney Uni, I was given the opportunity to do a small research project. And I chose to do that in astronomy. And I chose to do that looking at supermassive black holes, because by that time we'd had lectures on supermassive black holes and galaxies. I thought, oh, that sounds kind of cool. I'll do some research on that. And I really enjoyed that research project. It was very different to just, sitting in lectures, doing exams and assignments all the time. I like doing the research. So then I decided I'll do an honours year. And that's just one extra year after your bachelor's degree where you do half coursework and you spend a lot of time doing a research project. And again, I learnt more and more about black holes and galaxies and how to use radio telescopes. And I thought, you know what? I like this. Let's just do one step further. So then I did a PhD in astronomy. And that is all research. That's about 3.5 years of research. Again, I studied supermassive black holes, but there's a whole load of astronomy topics or other science topics that I could have chosen from. So after I had my PhD, I started thinking during my PhD, what did I want to do next? And it became more apparent that astronomy is very international. And so I then got a job working in the Netherlands as an astronomer. So I worked at a radio astronomy institute in the Netherlands for 4 years. And this is the building that I worked at on a particularly cold day. So this institute was in the middle of a national park in the Netherlands. It was a very interesting place to work. You could see, driving into work every day, there would be people, instead of walking their dogs, they cycle their dogs because they cycle everywhere. I thought that was interesting. And it was this quaint little village. You can kind of see the houses there. It just looked like it was out of a fairy tale. And I worked there for 4 years. And then in 2015, after my contract had finished in the Netherlands, I got offered another position back at Sydney Uni, and so now I'm back at Sydney Uni. And if you had told me when I was in high school that the concept of working overseas was just so foreign and so beyond my experience that the thought just never would have occurred to me. But now I've done it, and it's one of the best decisions that I think I've made in my life. So some of the things that I really like about astronomy, and this is what I just alluded to, I think my favourite thing is that it's very, very international. So just by being an astronomer, I've got to go to some amazing places. So I've got to use, high-tech optical telescopes. So this is in Chile, this one here. I've also been to the Canary Islands, which is here. They have these massive optical telescopes. Like I said, they like to build optical telescopes on top of mountains because that's where you get above a lot of the atmosphere. And they're also really unusual and interesting places to go and visit. I've been to, this is a radio telescope in Australia. As you can tell, they have kangaroos. So we're the only country that has radio telescopes with kangaroos. And this, believe it or not, is also a radio telescope in the Netherlands. It is literally just a stick that's stuck out of the ground, and it has all these electronics in this little circle thing at the top, and it can see all of the sky at once in radio waves. So we actually get images like the one I showed earlier from things like this. I've also got to go to lots of cool conferences to discuss my research and my recent results. So I've been to places like conferences in Rio. I got to go and hang out with some penguins in South Africa, the Galapagos Islands, Thailand. A lot of my holidays involve animals, I'm realising. But it's cool. I also like animals. So, the other thing that I really like about doing astronomy is that you're always working on something new. And this isn't just astronomy, but I think it's more science in general. So you have the ability to discover things and see things that no one has ever seen before. Also, I like the problem-solving aspect of things. I've always enjoyed problem-solving. So it's very detail-orientated. You get really focused on one particular problem, but you still need to be able to see the bigger picture. And the other aspect I like is that it's a very collaborative environment. You don't just go off and do your own thing, but you work closely with other people. You're always discussing your ideas and your results, and you're always talking to people about your science. And the last point I wanted to make is that studying science has brought me loads of opportunities. So I thought I'd just put a list up here of things that people who have studied science that I personally know have gone on to do. So I'm only listing jobs here where that I know, my friends that I'm still in contact with, friends that I made during either my undergraduate degree or my PhD, and what they're doing now. So some of them are still scientists. They work at places like CSIRO or ANSTO. I know people who are now working at NASA. Their job is to basically fly in a plane that has an infrared telescope in it, and it flies much higher than normal aircraft to try and get above the atmosphere. That's their job. I know people who've done a PhD in astronomy and then have made the connection to medical research. So they realise that some of the techniques that they learnt in astronomy is actually very similar to how an MRI works, and now they're developing a new way to do MRI. I know people who I did my undergrad degree with who are now doctors. They did a science degree and realised they really liked all the physiology, subjects and went, I want to be a doctor, so then they did a medicine degree after that. Data scientist is the new buzzword. Data science is kind of the new it job that all the big companies want data scientists, because they have all this data and they don't know how to deal with it. So I know people, working at Google, Qantas, Shell, Atlassian, small startups. I know people who started their own business, and then of course I know people who did science, they were really interested in science, and then they wanted to go and teach. They wanted to go and communicate their science, so they went and did that. I know people who did a science degree and then went into the banking industry and are earning lots of money right now. I know people who went into government. I even know people who've gone into consultancy. So this is not just a list of things you could potentially do. These are a list of jobs of people that I personally know who study science, and this is what they're doing now. So from my perspective, I have 3 kind of pieces of advice for you. My first piece is just study what you enjoy. If you enjoy maths and physics, or if you enjoy science, study it. Don't worry about, what's it going to be, what job can I get with this, because trust me, you can get loads of jobs with a science background. And this kind of relates to my next advice, which I wish someone had told me when I was in high school, is just take one step at a time. Make the decision that you need to make now. It's good to have goals, but don't try and plan out the next 50 years of your life. Life is long. You can't plan it all in one go. And related is to be flexible and open to new opportunities. So make the decisions that are best for you at the time, but be open to new opportunities when they come along. Okay. So my last slide, I just thought I'd advertise this Galaxy Convention if you are interested in doing STEM subjects. At the University of Sydney, we're holding a Galaxy Convention for women in STEM and entrepreneurship in December, I think. Yes. So this is open to high school students in years 10 to 12, and if you'd like to come along, you can sign up online, or you can talk to Jeanette, who's also here from Castrade. She's organising this Galaxy Convention, if you're interested. Okay, so I thought I'd leave a little bit of time at the end for some questions, if you have any questions about black holes or any kind of astronomy, weird questions that you want, or how I became an astronomer, things I like about my job. Anything you like. Yeah?
Remember when you were talking about the radio waves trying to get all the galaxy things? How long does that take, getting the data back into the...
So it takes the same amount of time. So say if you take, for example, Centaurus A, which is our closest radio galaxy, the radio waves travel at the same speed as the optical waves. So because it's 1 million light years away, it still takes 1 million years for that light to travel to us. But then once it's in our radio telescope, it takes, well, depends how complicated the data is, but it can take a few weeks to a few months to actually get an image. Yeah?
Are we close to developing any technology that will be able to see a supermassive black hole?
That's a really good question. Yes, surprisingly enough. So it won't be an image, it won't be like a photograph of a black hole. But what they've done, what they're working on now, is if you take all the radio telescopes of the world and you combine them all together, you can actually, so to zoom in to see something like the size of the black hole, you need a huge telescope. So the more you want to zoom in, the bigger your telescope has to be. And once they get to a limit of you basically need a telescope as big as the Earth, optical telescopes can't really become that big because then we would have nowhere to live. So what they do instead is something that is really useful. They use radio telescopes, and instead of making just one big radio telescope, they have lots of little radio telescopes, and they can combine them all together and basically fill in all the gaps. And that gives you essentially a telescope the size of the Earth. So they're doing that now with radio telescopes. They're trying to combine them all together to make the equivalent of a giant telescope to make an image of the supermassive black hole in the centre of our galaxy. So hopefully in the next few years we'll have an image of what a black hole actually looks like. But I don't know, has everyone seen Interstellar? So when they're passing Saturn or something and they see that black hole there. So that black hole, to make that movie, they actually employed an astronomer to do a computational simulation of what a black hole would actually look at. And because Hollywood was paying for it, they were able to invest loads of money into it and that's the best image of a black hole that anyone has ever seen in that movie. And actually, it was so interesting that the astronomers were able to publish scientific papers from that because they started noticing things that they hadn't thought about before. Yeah?
You know how you said that there's a supermassive black hole at the center of our galaxy? Will it affect us?
No. No. It is so far away and so small and distant compared to where we are in our galaxy that it has very little direct effect on us. It has an effect on the galaxy as a whole in that, it kind of keeps the galaxy together and keeps it rotating. So it keeps our kind of, solar system in its place in the Milky Way. But it's too small and too far away we're not going to be sucked into the black hole anytime soon. You don't have to worry about that. Yeah, you had a question?
How will getting an image of a black hole advance our learning?
Wow, that's a really good question. I don't actually know. So, that's one of the great things about science is that you don't always know what you're going to find out. So it's all about exploration. I think it will tell us what happens on the black holes at those very small scales. So we can see, the only way that we observe black holes now is by looking at either the stars that orbit them or, these accretion disks, and we see the effect that it has on the material around the black hole. But we can't see what's happening right close to the black hole, basically what we call the event horizon, which is the border of the black hole. So an image of a black hole might give us more information about what's actually happening, how the event horizon works, and how black holes, do they become bigger when gas and stars fall in the black hole, or what happens to them. But there's a lot of unknowns there. Yeah.
Are they actually called supermassive black holes?
Yes. No, astronomers are incredibly unimaginative at coming up with names. So yes, they are called. I have published papers with the word supermassive black hole in it a lot of times. So to give you an example, one of the optical telescopes. So the optical telescope is one of the really popular ones. One of the biggest ones that we use at the moment is called the Very Large Telescope, the VLT. The one they're building, I'm not joking. The one they're building, the next biggest one is going to be the ELT, which stands for Extremely Large Telescope. We are terrible at coming up with fancy names. But on the other hand, I kind of like it because when I say it's a supermassive black hole, you know exactly what I'm talking about. It's a really, really big black hole. Yeah.
So I have to do astronomy, but how did you get into your course? Did you get the ATAR that you wanted and stuff, or did you have to
Yes. Yeah. So, I did do 4-unit maths. Actually, when I was doing 4-unit maths, we had our first assessment in year 12, and there was a small class of us, about six of us or so, and the teacher kind of said, maybe not everyone can do 4-unit maths, maybe some of you will have to drop down to 3-unit maths. And I looked at my test result, and I got the lowest of that exam, and that immediately was screw you, I can show you, I will do 4-unit maths, and I will show you. And then I ended up almost topping the class. So I'm incredibly stubborn. So as soon as someone told me you can't do 4-unit maths, I was like, yes, I can. Let me show you. So that helped with my ATAR. I actually found, because I applied for a double degree, science and arts, the ATAR for that was actually, I think, lower than just getting into a science degree. So that also worked out well for me. And then I dropped the arts bit later.